All right, so basic heating controls. Again, we're going to keep going into this and pretty much finish up everything going on with chapter 13 for our heating control devices. Um, for one of our most basic controls we looked at right before our break was the fan switch. Now that the fan switch has got it where it's actually going to have the control over the blower fan. That's what we're talking about. Oh gosh, I keep forgetting to take my glasses off. Can't see my own eyes when I'm looking at the screen. So the limit switch, its whole idea is to set a limit. Honestly, HVAC, we have some really complicated names for stuff sometimes, and then we've got some really simply named stuff for things sometimes. And a limit switch is one of the simple times. So it makes sure that the heat does not exceed whatever it's set for. You know, for most gas furnaces, it's going to be set to about 200 degrees. If the temperature gets above 200, it's going to shut the system down. Boilers have a similar limit switch that they use to make sure that if the water temperature in a boiler gets too high, about 200 degrees, that boiler will shut down and stop trying to boil that water, try to stop heating it up and everything like that. So a limit switch is really just there to make sure that we don't get to an overheating scenario, or to make sure that we don't have heat where it's not supposed to be. Gives an example here at the bottom, talking about a flame rollout switch. So a flame rollout switch is basically, you'll have your burners set up to fire gas and flames in a specific direction. But if it starts going in the opposite direction, it's called a rollout, and the flame will actually hit a sensor, and that sensor will deactivate the system and will shut it down until it knows that it can fire off that burner again safely. And that's what it's looking to do. When we're dealing especially electric heat, not a huge number of safety issues or precautions you have to worry about. Electrical fires are about the only one with that, which comes down to properly gauged and gauged and maintained wire. Basically, make sure that the wires are the proper size and they're not damaged. That'll prevent electrical fires. But for our high temperature with the gas and oil furnaces and heat and everything like that, what we're dealing with a lot of times is an excessive flame. And that already is starting off with a lot of things that can go wrong with the combustion process and can lead to fire starting where it's not supposed to. The electric heat will have limit switches as well, because it will eventually damage itself if it overheats. It will actually damage the metal that makes up the electric heat pack and the coils and everything. So again, limit switch, just there to set a limit, say, hey, this is the max we're going to go. It will shut the system off. As far as the heating system, it will typically allow for that fan to stay on, to move air across it to cool off that heat exchanger, those coils, whatever it might be that's overheating. And then once that limit switch, though, once it sets back, it's going to be ready to go and fine. Limit switches, you're going to see, they're going to look, the symbol for them, it's going to, as far as the temperature limit switch, is going to look exactly like you would see for a heating thermostat. It's going to be a closed switch for temperature that will open on a rise. So as temperature increases, that'll move up and that will open, and that will disconnect your power. Let's say this would be for your 120, and you've got your 120, and this is from our source, and this is going to our load, you know, and basically what we're doing is we're cutting off the power to our loads, to our devices, to stop them from turning on. That's all the flame rollout switch is really going to be looking like. All right, so pressure switches. These are used in pretty much every type of gas furnace nowadays. Y'all learn about, there's a couple of different things with gas furnaces that's a little weird. So for heating, you're always going to have it where three things have to be present for combustion to take place, for heat to actually be produced. You got to have fuel, I'm just putting a single letter, fuel, oxygen, and heat. I'll at least write that one out. Oh God, maybe I shouldn't have. Fuel, oxygen, and heat. Those three are going to be required for you to have heat, to have combustion take place. The heat can be heat from a spark ignition, could be from a hot surface igniter, whatever it is. Our fuel can be natural gas or propane or fuel oil. And the oxygen we're going to get from the air that's around the burner. Now, one of the things you got to make sure, though, is you got to make sure that when you have this combustion take place, that you can get the flue gases or the exhaust gases coming off of that out of the system, out of the way. You can't, if you're not getting rid of the exhaust gases, those flue gases, it's going to be like running a car in a garage. You're going to build up carbon monoxide in the house, and you're going to kill everyone. That's exactly what would happen. So to avoid that, because I don't know about y'all, but I think one of the minimum requirements of an HVAC technician is to not want to kill people with air conditioners and heating equipment, and to ensure safety. It's like minimum level, just my opinion. But we've got it where the inducer draft motor is an actual motor that all its job is to make sure that those flue gases, those exhaust gases are forced by a fan out of the house. They vent it, everything out of that house. But to make sure that that fan's actually operating, we use a pressure switch. So that fan will come on first thing, and to tell the system, yes, we have the fan coming on, what'll happen is you'll have a pressure switch that will close on a drop in pressure. So it'll be a normally open switch. And it'll look something like this. Little half circle is for pressure. And this means that it's going to open on an increase in pressure, and as the pressure gets decreased, as that fan operates, it's going to pull a vacuum. It's going to pull pressure down inside of the chamber. And when it pulls that vacuum down, that tells the system, okay, we've got enough air velocity, we've got enough speed for this airflow to make sure that all those flue gases are going to get out of the house. Otherwise, it's not safe and we can't operate properly. So once that switch closes, this is what's going to tell the system to start, hey, go ahead, get the igniter going, and it's going to start this whole process in order of operations for a gas furnace. You'll learn more about that order and how those switches work and how to test them when you get your gas furnace class, which is one of the classes I'm teaching currently right now. We go into detail about all of the different aspects of that gas furnace. But the main thing to understand is this is to make sure this pressure switch is only there to make sure, can we get all the flue gases out of the structure safely and without having to have any issues. These can go on you. It's pretty common for one of these pressure switches to go bad. They're not super hard to replace as far as these ones are concerned. They work really well, but it's just a matter of, finding the right one and making sure it's the correct size and type and everything like that. That gets difficult sometimes, because I've had it before where there will be new style pressure switches that come in a plastic housing that are the size of $50. And then I've got other ones where it's, a 4-inch diameter, massive disc, that's all metal. But it's the same exact part. It does the same exact job. It's just different design and how old the unit is versus how new it is. So these will be, you know, these are going to be used all the time, especially for safety devices. Other things we're going to see for gas heating controls are going to be things like our initial thermostat, you know, having a call for heating. And we've got a couple of things with that that'll be operating. So as far as a gas burner is concerned, you've got 3 different types of ignition. You've either got a standing pilot, which is your old school. If you've ever had to relight your pilot on a water heater or an oven, or maybe your furnace or a boiler, that was probably a standing pilot. That's that old school. You have to press a button down and it's going to push gas to a little flame, and you take a long stick like barbecue lighter and you stick it down in there and you light it right by there. You press that button, you wait for it to catch by itself. Basically, the idea is with a pilot, whether it's a standing or an intermittent pilot, it's our source of ignition to light up the rest of our burners is a tiny little flame. We'll just have a tiny little flame going, and then that'll ignite the rest of our burners. The reason why is because the amount of temperature required to cause ignition is about 12 to 1400 degrees Fahrenheit. It's a lot of heat. Now, that heat can be generated by that electronic spark. If you've ever had a gas stovetop and you clicked it on, that click, 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 that when it first ignites, that's 12 to 1400 degrees, that tiny little white electric spark, that arc. It's a very, very high temperature. So we've got things like that that are newer style controls, but old school back in the day, the only thing that we could consistently get to that high temperature and high enough to cause ignition was to just start a flame ourselves and to keep that flame going all day long. Intermittent pilots work off the same idea. We're going to use that flame to ignite the rest of our burners, but they allow for an automatic source of ignition, whether it's one of those little spark igniters or a electronic ignition of some sort, to ignite just a small flame first. And then once that small flame is on and it's been proven that it's on, then the rest of the system will, okay, turn on the rest of the gas and get the igniters going and get the rest of the burners going. And that's what you're going to see pretty much for your older systems. Everything just about nowadays is switching to direct ignition, where it doesn't have a pilot light at all. And the reason for this is because if a pilot light goes out, it's a pain in the butt. It's not easy to fix. It's not, if it's a constant problem, it's a real pain, you know, as well. To make it so that it's less parts to troubleshoot and a lot simpler, and a customer doesn't have to worry about relighting their pilot, newer systems just forego the pilot and just ignite all the burners at one time. They start with the first and then they carry that chain right down the line instantly. So direct ignition, you've got 2 sources typically, either hot surface igniters or what are called HSIs, or direct spark ignitions, or DSIs. So that's typically what you're going to see. Again, you'll learn more about those when you get to your gas furnace class, so I'm not worried about you knowing those right now. All right, so this picture right here is a really good example of a gas heating system. So you can see there's this silver tube down here. What it's going to be, that silver tube is actually going to be our gas line. And that's going to carry a small trace amount of gas down here to this end. And there's a little tiny burner. And it's going to, and you're going to have to manually ignite that burner for this system. At least I'm pretty sure this doesn't have a spark ignition. It doesn't look like it. And what's going to happen is that flame will be ignited. And then this right here on the end, this will change depending on what kind of system we've got. This looks like a sensing bulb for this one, as far as this picture is concerned. But right in front of that flame, we use a number of different controls to prove that that flame is there. One of the things is going to be a thermocouple. And a thermocouple works a really unique way. You've got it where inside of every flame, I don't care if it's on a stovetop, out by a campfire, or in a furnace, every flame produces a small trace amount of electricity. Now, that electricity, if it's harnessed, can actually be used to do different things. So for a thermocouple, for us, what it does is that flame is sitting right there, and that flame is going to heat up that thermocouple, and that thermocouple will send a signal down of millivoltage, and that millivolt signal will get to the board, to that integrated furnace control board, to that direct digital controller or solid state device, and it will tell it, hey, here's a little signal of voltage coming from this thermocouple, and where it's plugged into the system will know, oh yeah, we've got a flame, we're safe. The reason why it does that is because if it doesn't have a flame, then it will get no signal, and then when it gets no signal and we don't have a flame, it won't try to ignite. It won't just be throwing gas into a chamber without igniting, which is much more dangerous. It's just to have natural gas build up into a space. We've got a couple of different ones that we'll see for these, but again, standing pilots with a thermocouple, pretty common to see. The intermittent pilot, like I said before, it's going to have it where it can ignite its own pilot, and then the burners will ignite, but it's still going to have a thermocouple or some sort of temperature sensor sitting next to that pilot flame to ensure that, yes, the pilot is on. The nice thing about these is the pilot doesn't come on until there's a call for heating. So it's not even like it has to stay on during the whole heating season. It doesn't come on until that thermostat says, hey, it's gotten down to 66 and we're set at 67. Ignite the pilot and start the burners. That's when that's actually going to first come on. So, what else? Yeah, that's pretty much it for the intermittent pilot. It's going to be the same exact thing as a standing. It's just going to, instead of us having to manually light the pilot, this automatically lights its pilot itself. Oh, here's a much better picture of that up close of everything. So this would be right here. This on the right is your burner and everything. So this is a terrible page for this to be on. This is part of a intermittent pilot ignition system, even though it's on the direct ignition burner control system. So you would have it where the gas would be burning right here. All right, and then this little flame sensor right here is what's going to convert the temperature that's going to come out of here with this flame, and it's going to convert that to electric signal down here at the bottom. Depending on the style of them, you'll actually have where they can be used not only as the temperature sensor, but they can be used as the spark igniter as well. Which helps make it so that you've got less parts, less things you have to replace, and then your ignition control can be used for more than just, okay, can we light a pilot and make sure it stays lit? No, we can light a pilot and make sure it stays lit, keep relighting it if we need to, all that kind of stuff. It's pretty sweet how these kind of comboed systems work together. Because it's the idea of, well, if that works good for that one and this works good for the other, why not combine them and see what happens? Which makes sense. So integrated furnace controls, again, IFC boards. This is what you're going to see typically for most furnaces nowadays. They're going to have a control board on them, if not multiple. And it's going to control your ignition process, your inducer draft motor, your blower motor, everything about that. It's going to control all the aspects, the timing, the temperatures, everything, when it turns on, when it turns off, how everything's going to be operating. So that's really all that's going to be talking about as far as the IFC board. For oil heating, the main thing is to understand that we've got it where it's going to be that CAD cell control. But the oil heat, more than a gas heat, is going to be very cautious about when it throws fuel into a heat exchanger, right? If we're dealing with natural gas or propane, there's a benefit. Natural gas and propane are a gas. So if I put a gas into a chamber and it doesn't burn up and it kind of just sits there, it doesn't go anywhere, you know, eventually it'll dissipate out into the air and it'll mix and it'll, you know, I might smell a little faint, you know, a bit of rotten eggs, but I'm not going to have it where I'm going to have to worry about that, you know, gas getting stuck in the heat exchanger. For an oil furnace, it's dealing with liquid fuel, dealing with diesel, you know. That liquid fuel, if it goes through the burner nozzle and it doesn't ignite, then it can coat the inside of the heat exchanger with oil, with that diesel, and this leads to some big problems. One of the most common things used to be back in the day, a lot of trailer parks used oil heat because it was cheap. Nowadays, it's not as cheap as it used to be, just because fuel costs have gone up and up and up over the years. But you would see oil heating system used a lot in trailer parks. And what would happen is you have a reset button on an oil furnace. So if it doesn't ignite, someone can go down and press the red button and that'll reset it. But what it does really is it tries to ignite again. So the nozzle sprays fuel into the heat exchanger again. And if it doesn't have ignition again, then it just coats the inside with more of that fuel oil. And this can cause a number of issues. One of them being the fact that the fuel oil inside of that, if you have it where a technician comes out and they don't realize that they've been trying to ignite and they haven't gotten any, well, they've just basically built up a level of liquid oil or liquid fuel in the bottom of their heat exchanger. Now, I go to fix it, I ignite it, I get it going. The flame will start, but what's going to happen is that collected diesel at the bottom, the fumes will first ignite, and then as the fumes ignite, it's going to heat up that diesel, and that diesel is going to turn into fumes all at once, and then all at once it turns into flames, and then you basically just have a bomb go off. You just exploded a house apart because someone decided they were going to reset their fuel oil system again and again and again. This is one of the big reasons why these systems really have to control how many times you can reset it before it'll just shut itself off, and how it can be reset. You know, is it something where you can just flip a switch? No, you got to go down to the unit, know what to look for, know what to press, everything like that. It's not super simple. So oil heating, it's really just to make sure that we're not causing an unsafe situation to occur, because it's much easier when you're dealing with a liquid fuel source as opposed to a gaseous one. Gas is going to eventually dissipate. Oil is going to stick around. It's going to stay there. The other thing is that heat exchanger, it'll coat the inside of it with that fuel oil, even if it's just been sprayed a couple of times. And then when that fuel oil eventually burns, it'll burn off all that stuff that's been coated on the inside, and it'll create weak spots and hot spots in that heat exchanger and make it so that it's not going to heat evenly. It'll actually heat unevenly and can cause the welds and the connections on everything to actually rupture and break apart. And then you have it where you got a cracked heat exchanger, and now you got to get a new furnace. So again, CAD cells, they're going to be the main primary oil safety that we're going to see nowadays. The only other style you saw back in the day was what's called a stack switch. Stack switches are really not used anymore. If you find a stack switch while y'all are out in the field, please bring it back to the school, because we would like to have one. Not even joking. It's that old of equipment. They stopped using stack switches in about the 70s and 80s. And since then, pretty much every oil furnace has been replaced with new CAD cell control systems. So stack switches, again, old school kind of way to do it. But the CAD cell is really cool. It just looks for light, because there's no fire that you're going to have that doesn't produce some amount of light. Find one that does, that'd be cool. Figure out a fire that produces no light, like a black light fire or something like that is all I'm thinking about. But even then, it's still providing some light. So this CAD cell is really just, that's all it's going to look for. Common problems with them is really just going to be that the CAD cell can get dirty. It can build up soot and all sorts of stuff on top of it, so just clean them off every once in a while. That's all you got to do for them. Make sure they're working right and clean them off. So this is what I was talking about before, stack switches. If you come across one, it's ancient technology, not just old, ancient. Basically, it was a set of bimetal switches that would, so we would check and see if we had ignition with a CAD cell by looking at the light from the flame. The stack switch is a switch placed in the flue piping as the exhaust gases are leaving the building, and right near the furnace is where it's located, and it will sense the temperature of those gases, and if it's hot, if those gases are hot, then obviously there's a flame, so keep on pumping fuel oil and keep on burning fuel. But if it remains cool, then it knows, okay, we're not having a flame, we're not having heat production, I'll go ahead and shut the system down from operating while there's no combustion present. Again, it used a number of bimetal strips, basically, to move and create contact or disconnect contact based on how hot the temperatures in the flue gases were. So electric heating controls, we've got a couple of different things that'll be unique to these. This is what an electric resistance heater is going to look like on the back side of it. On the front side, it's just you're going to see these little white tabs, basically these connections where the wires can go into. But on the back side, you can see basically electricity is going to flow in. It's going to go through this tight coil of wires, and that coil of wires is going to heat up. It's going to turn bright red, just like you would have if you have ever cooked with an electric burner. You've seen them where they start going bright red. It's the same technology we're using right here. Same exact technology. Imagine if you took the cooktop burner from your electric stove and you stuck it right here inside of your ductwork and you turned it all the way to max and you blew a fan across it. It's basically what you're doing here. These are a little more sophisticated and more designed for heating and air conditioning application than your stovetop burner would be, obviously, but basically it's going to have it where this is a very, very common source of heating in Virginia as well. So I mentioned during our last set of slides that the heat pump is one of your most common sources of heat in Virginia, and that's because we're at that sweet point for where a heat pump can operate as far as climate is concerned. The second most common type of heating is the emergency heat for a heat pump, which is most commonly electric. Because if you're running a heat pump, you don't need to have gas necessarily at the house or at the structure. So they might not have a natural gas line. They might not have a propane tank or anything like that. But that electric heater, what it's actually going to do is it will it'll increase in temperature, and then this will make it so that we have a backup source of heat without having to worry about getting gas to a house or anything like that. So if we've got a heat pump and all they got is electric as far as their appliances, they can't get gas lines running their house for whatever reason, having electric resistance heat as your emergency heat just makes sense. It works out the best for us. It's what really knocks it out of the park as far as our excuse me. It really knocks it out of the park as far as emergency heat is concerned for a heat pump. It can make up the same amount of heat without having to require a huge amount of space. The only problem with electric heat is it sucks up power like crazy. So when that emergency heat kicks on, yeah, sure, we're staying warm, but it's costing us a pretty penny. But again, the whole idea behind it is to really just be a secondary source of heat for a heat pump is what you're typically going to see electric heat used for. Now, you will see where furnaces are designed and systems are designed where the only source of heating is electric heat. They don't have heat pump with electric heat. It's just electric heat, and that's all you're going to see. Basic thing with a electric heat system that we'll use as far as controls is a sequencer. All right. Now, a sequencer is going to be a switch that will turn on devices in a certain order. So, and it will turn it off in the backwards order. So if we had sequencer 1, 2, 3 hooked up to heater strip 1, 2, 3, you would have it where it would turn on the first one, wait a little bit of time, turn on the second one, wait a little bit of time, turn on the third one. Then once the heat is satisfied, it'll turn off the third one first, then the second after a little bit of time, and then the first after a little bit of time. Sequencers are really, really cool. Y'all will be able to see those when you do your heat pump class. We'll actually have you wire up and make connections for a heat pump, basically for a defrost cycle and an emergency heat cycle. So you can see how all of those things would be connected together. So sequencers, again, really common thing that you're going to see for electric heating most of the time. Other form of heating we're going to see is hydronic and steam systems. Pretty much hydronics, it means hot water or steam. This is just repeating itself. When it says hydronic and steam, it could just say hydronic controls. But you've got a number of different controls that are unique to hydronic and steam systems. For a hydronic boiler system, you're going to see, let's see if it goes into it. Yeah, okay. So you've got a couple of different things you're going to see for them. One is going to be a low water cutoff, where if it's not got enough water in the system, it will shut the system off. The water temperature limit is your most common thing that you'll see on pretty much every boiler, because if we're just trying to have hot water and not steam, we cannot let that water get to 212 degrees. So typically for the water temperature limit, it's going to be, once it gets to about 200, it shuts the system completely off. And you got flow switches to prove and allow for the flow of water and saying, yes, we've got heat, we're getting water, we're good to go. Again, steam systems are going to be very similar to hot water systems. They're going to have a few other controls. So for a hydronic hot water system, the water temperature limit or the water temperature will be set by what's called an aquastat. Right? An aquastat is just a thermostat that sets temperature for the water in a boiler. That's all it does. For a steam system, you use I haven't worked on a steam system so long. It's a vapor troll and pressure troll and vapor stat. That's what it's called. So the pressure troll is it's a control making sure that the pressure of the steam does not exceed what the pipes can handle and everything like that, what the system is prepared to deal with. We'll also have a pressure sensor and control on a hydronic system that will open up the system and allow water to drain out. If it gets to too high of a pressure, it'll just get out of the system. So vapor troll and then the pressure troll and the vapor stat. Vapor stat, you can guess what that does. It keeps eye on the temperature of the vapor of the vaporized water, which is steam. So it just keeps an eye and make sure that's staying well above 212. Hydronic systems, again, we've got most of them. It's going to be something basically in the water or in the steam lines, checking temperature, checking pressure, making sure that we have hot water and hot steam going where it needs to. So there's a lot of different controls going on with that. But again, heating systems, whether it's steam, whether it's hot water, whether it's oil or gas heat or electric or a heat pump, they're all going to be requiring a lot of different controls, a lot of different devices to make sure that they are staying on, that they're operating safely, and that they're operating efficiently. That's pretty much it for the night. So we finished. We got 5 minutes. If y'all got any questions, please let me know. All right, I'll go ahead and get this ended then, and I will upload the videos and send them out for y'all so you can review them if you want to or anything. And I'll see y'all again on Monday.